Hello guys, and welcome to another calculus video. In this video we're on video 2 out of 4 on our So in this video we're going to be covering Laurent series, residues, and the residue theorem, which are all very important in the calculation of contour integrals. So let's go ahead and jump right into the lesson. So first off, we have to discuss what is a Laurent series. When we're dealing with real numbers, we'll generally use what's called a Taylor series, which is just a series of terms multiplied by powers of x minus x0, where x0 is the center of the Taylor series. And these will have a radius and interval of convergence and all the sorts of things that we're used to. However, when we get to complex analysis, we actually use something else we called the Laurent series. And the reason we use this is so that we can choose our starting point for the series to be anywhere we want, even a point that has a singularity. And so a Laurent series will have it'll have a Taylor series, first of all, within the Laurent series, and it'll also have terms of negative degree. Now, these terms of negative degree, when you add them all together, are called the principal part of the Laurent series, and they are very important. So the Laurent series will start at some Bn, and that Bn will correspond to the order of the pole at which we're doing the Laurent series. So for example, if we wanted to calculate the Laurent series of 1 over z at z equals 0, then the Laurent series would just be 1 over z, right? So we have a first order pole, and our first term is just going to be b1. However, if we have a more complicated function, like for example 1 over z squared with z minus 1 to the third power in the bottom, then if we wanted to create the Laurent series around z equals 1, we would have a b3 term, and then a b2 term, and a b1 term, and so on and so forth, right? So the first term, or the term of the highest negative degree, is going to correspond to the order of the pole. Some Laurent series may have an infinite number of terms of negative degree, and this is called an essential singularity, which we'll get to later in the video. And most importantly, the residue of the function of a function f of z at the point z0 is just the coefficient of 1 over z, which is the same as b1. So this number b1 is super important in complex analysis, and it is called the residue of f of z at z0. So of course, we can calculate the Laurent series of a function at many different points. So the residue is not a value only of the function, it's also a value that's dependent on the point at which you're taking the Laurent series. So one function may have multiple residues. So why do we care about residues? I'm going to show you why residues are so important. We're going to consider a contour integral over a curve gamma of f of z dz. This is a closed contour. And the point that we're worried about here is we're going to center our contour integral about a pole of some function. And we're going to let our radius of this circle, which makes up the curve gamma, be r. And this is going to be a perfect circle. One important thing is that this radius r is small enough such that our this pole is the only pole or singularity of our function that falls within the circle, right? So this r can be arbitrarily small or large as long as it satisfies that requirement. And this is the point z equals z0, which is a pole of the function, as I said. And interestingly enough, we can actually describe this circle by z equals z0 plus r e to the I theta. So we're centered at z0, we're r distance away from the center, and e to the I theta is just going to trace out a nice little circle because of the trigonometric properties of e to the I theta. And so theta is going to go from 0 to 2 pi. And what this means is that we can actually use this expression. Since theta is going from 0 to 2 pi, we can convert this contour integral into a normal integral. So if we calculate dz dependent on theta as our variable, we get that dz equals I r e to the I theta times d theta. Sorry, I missed that d theta in there. I was going back and checking. So this is all d theta. And then we're going to use the representation of f of z as the Laurent series. So I just have a and bn have been combined to just be cn, as n goes from negative infinity to positive infinity. So when we go ahead and substitute this in, this looks very daunting, but we're just going to go step by step. We've taken the summation outside of the integral because we're just considering the effect on each of the individual terms. So we get cn times the integral from 0 to 2 pi of r e to the I theta, which is just z minus z0 to the n, right? All raised to the n power plus I r e to the I theta d theta. then once we separate the r's and the I thetas, we're going to get this. R to the n plus 1 times I e to the n plus 1 I theta d theta. Then when we integrate this with respect to theta, as long as n isn't equal to -1, because if n is equal to -1, then we just have e to the 0, right? So let's not consider that one right now, but for all the other values of n, we're just going to end up dividing by n plus 1 times I and evaluating it at 2 pi and 0. And what this means is that this term is actually, all of these terms except for the -1 term are going to go to 0, because when you evaluate this function right here at 2 pi and at 0, because theta is 2 pi and theta is 0, and this is just an integer, where it's going to be a multiple of 2 pi, and e to the 2 pi I is always just going to be 1. So it's going to be the same at both bounds, and so it's going to be 0. However, for n equals -1, we're integrating I times d theta from 0 to 2 pi. And of course, we also have this coefficient c -1, which, as we know, is the residue of the function at z0. And when we integrate I d theta from 0 to 2 pi, we just get 2 pi I times c -1, which is the same as 2 pi I times the residue of f of z at z0. And this is incredibly helpful because the residue can be calculated without calculating the integral, which makes the integral much easier to calculate. And this leads us directly into the residue theorem, which is the basis of most contour integration. So the statement of the residue theorem, this is a shortened version, but it's the only version that we're going to actually need. If gamma is a positively oriented, meaning it goes in the counterclockwise direction, simple closed curve, then the contour integral of f of z dz over gamma is going to be equal to 2 pi I times the sum of all the residues of f of z at points zk, where zk is all these singular points inside of gamma. So if we have some closed curve, all we need to do is find all the singular points, find the residues of the function at all of those points, add them together, and multiply them by 2 pi I, and that gives us the value of the contour integral. Also, simple closed curve does also require that the closed curve does not intersect itself, so that's important. So let me go ahead and show you it's not necessarily a proof, but just a demonstration to how this actually works. So we're trying to calculate the integral over this curve gamma, which I've just made a circle of f of z dz. It has some residues on the inside here. So the way we're going to do this is we're going to consider a second curve, gamma 1. Now, gamma 1 is the same as gamma. It has this counterclockwise oriented circle right here, and it also has these clockwise oriented circles around each residue. And these circles can be made as small, as large as you want, as long as they only enclose the residue and no other residues or singular points nearby. Or sorry, not residue, poles. They only enclose those poles and no other poles nearby. And based on what we talked about last video, since these are negatively oriented, or they go in the clockwise direction, we actually only count all the area outside of them. So we're counting all of the area inside of this outer curve, but outside of these curves. And since our function has no poles, and we're only dealing with analytic functions here, then since everywhere in this area is analytic, since we're not dealing with the poles right now, by Cauchy's first theorem, or Cauchy's integral formula, which we discussed in the last video, this entire integral just goes to 0. So this gamma 1 integral goes to 0. Then we also consider this gamma 2, which is this curve where it's pretty much just the opposite of these three circles, it going in the clockwise direction around each of these poles. Now notice, if we add the integral over gamma 1 and the integral over gamma 2 together, we just get gamma again, because positively oriented, negatively oriented, they cancel with each other. And we can split up gamma 2 into these three separate integrals of these small circles, and they're actually the exact same integrals that we calculated earlier. It's just a small circle around a residue, or around a pole, sorry, which is just going to be 2 pi I times the residue of the function at that pole. So that means that our entire contour integral, which remember was the integral over gamma right here, is going to be 0, which is the contribution from this integral, plus the sum of the residues of f of z at all the poles within the integral, which is exactly what we just stated before. So as you can see, it's not too difficult to see why the residue theorem works, as opposed to some other theorems that might be a little bit tricky, but as you can see, it's not too difficult to understand why it works here. So let's go ahead and figure out how we can calculate residues. So residue calculation is really easy. If z0 is a pole of f of z of order n, now I know this looks really daunting, but it's not too difficult. the residue of f of z at 0, 0 equals 1 over n minus 1 factorial times the limit as z goes to z0 of the n minus 1th derivative of z minus z0 to the n times f of z. Now this looks really daunting, but trust me, we're never going to deal with high values of n. I shouldn't say never, but it's very unlikely you're going to deal with high values of n. And really all you need to do is plug in this formula, and this is all very basic calculus that anyone in Calc BC could do. Now, the more tricky part is a challenge problem that I'm giving you guys, which is to prove it using the Laurent series of the function about z0. And that seems really difficult to prove, this crazy formula right here, but trust me, it's a lot easier than it looks. All you have to do is plug in the formula for the Laurent series and show that it actually evaluates to the residue. So, I think you guys should definitely try that. Now, the issue with this is that this requires us to know the order of the pole. And there's something called essential singularities that we talked about before. And we can't use the derivative trick because with an essential singularity, it's equivalent to essentially having a pole of infinite order. So what this is going to look like is, for example, the function e to the 1 over z at 0. If you were to expand it as a Laurent series, you can see that as n grows large, we just have z to the negative n, so eventually we'll get to like z to the negative infinity. And as you can see, we have an infinitely large pole order here. However, that's not actually a big problem for us. We can't use the derivative trick because we can't multiply by z minus z0 to the infinity and take the derivative infinity times and then divide by infinity factorial. That doesn't work. But what we can do is calculate the using the definition of the actual residue. So in this case, it's super easy. We use a Taylor series. So in some cases, you may need to use Laurent series, but in this case, we can just use the Taylor series for 1 over z. We get 1 plus 1 over z plus 1 over 2z squared. And remember, the residue is simply going to be the coefficient of 1 over z, which is just 1 in this case. So that's super easy. I just think that worked example makes it clear how easy in general it's going to be to calculate the residue at a essential singularity. Now, in some cases, if you have multiple functions multiplying each other, it can get a little tricky, but I think you guys, I don't think there are going to be many situations where you're going to have to do something like that. So just remember, use the Taylor series and directly find the residue by finding the coefficient of 1 over z. So here's our summary. To calculate the value of a contour integral, and this applies to any contour integral for a meromorphic function. And meromorphic functions are not something we've discussed before, but essentially it just means this function, a function being meromorphic just means that it's analytic everywhere except for a set of isolated points. So those are our singular points or our poles where we're going to calculate the residues, right? So some functions that aren't meromorphic are stuff like natural log of z, which has a branch cut, which is something we'll discuss later, or functions that just aren't analytic anywhere, like the modulus of z. So to find the value of any contour integral of a meromorphic function, the first step is to find the singular points. The second step is to find which singular points are within the contour, because you need to only consider those ones. If you consider points that are outside the contour, then you're going to get a value that does not match with your contour integral, and then simply find the residues. So let's go ahead and do some practice problems. So I have a bunch of practice problems right here just for calculating the residues of the function, so I'll go ahead and put those on screen. I absolutely think you guys should try these. So go ahead and pause and try these. Sorry, this right here I kind of screwed up. This says log of z, which is the same as natural log. We just will typically write log in order to, in complex analysis, we usually use log rather than natural log. And I also have some practice problems here on the residue theorem. So all of these are using the contour gamma, which is this curve where we go from negative r to positive r on the real axis, and then we come back on this big semicircle. This is a very important contour, as this is the basis of most contour integrals that are useful to us when we're solving definite integrals, so that's why all the practice problems contain this. So here are 4 practice problems with that curve and with some other curves right here. Go ahead and pause and try these. And I have 4 more practice problems right here. Number 8 is starred because it's an exceptionally hard practice problem. You absolutely do not need to know how to do this, but I think it's a fun challenge problem with an absolutely magnificent result. So go ahead and try these. And I'll show you that number 8, the contour right here, is this curve gamma, which essentially it's enveloping all these residues, all these poles of gamma of z, because there are infinitely many. So we're taking the limit as r goes to infinity, so essentially we're just saying it's going to envelop every single pole of gamma of z. So hopefully you guys tried all of those practice problems and got some practice, and if there's anything you still need help on, I'm absolutely free. Yeah, go ahead and join the Discord and ask me any questions you want, and let's go ahead and go over what's going to go on the next video. We're going to cover a lot of things in the next video, so it might be a little bit of a long video. We're going to cover the estimation lemma, Jordan's lemma, parametrization of straight line integrals, small circle integrals, and possibly branch cuts and points. Oh, sorry, I have a typo there. But I think that I may have to postpone that to a next video, so we may end up having 5 videos in the series. I'm not entirely sure. But yeah, so we're going to cover a lot of things, and essentially by the end of that video, you'll be able to evaluate nearly any contour integral, excluding those with some crazy branch cuts or higher level concepts. But after that, the 4th video is just going to be on strategies for using contour integration in order to actually solve definite integrals. So, I hope you guys enjoyed the video. Please let me know if there's anything I can do to improve your experience. Thank you, and I'll see you next time.